Now here, again, we see our elementary matrices E1 through E6, and we multiply E2 times E3 times E1. Now, associativity, we understand that the matrix multiplication is associative. You should know how to prove that. But if we want E1, E2, E3, E2, E1, if we want to do that product, we have to pick two of them to multiply together first. And it can't be E3 and E1. It has to be two that are right next to each other, because remember, commutativity would get in our way if we tried to do this first. Then we wouldn't know which way to multiply it by E2. And it simply wouldn't work. It wouldn't work reliably in any way. Okay, so we choose to multiply. Here are the matrices, E3, E2, E1. We multiply E2 by E1. And I'm not going to go through the details of the multiplication. You can verify that if I multiply these two matrices, I get this. Then if I multiply on the left by this one, you can verify that we get this. Okay. Then we do E6, E5, E4. And I simply assert that that equals this. And you can verify it. Multiply E4 on the left by E5, multiply that on the left by E6, so that the product E6 down through E1 would be this times this, which you can verify gives you this. At least I hope it does. I'm not sure. It's been a while since I've done this, and I'm not sure how tightly I verified it. Now if we want to test that, we just multiply this by the original matrix A, which is way up here, and I'm not sure you can see it, but we could actually do that. And I'm going to take the time to just write out the product. 1/2, -2, 5/2, 0, 3/2, -2, 0, -1/2, 1. You can't see me, of course, because I'm blocking the heck out of the board. Okay, and we multiply that by the original matrix, which is 2, 3, 1. Um, 0, 2, 4, 0, 1, 3. And I don't know if this is going to work. It looks to me like maybe it won't. But let's see. Okay, multiply this by the first column, we're going to get 1. Multiply by the second column, 1/2 times 3 is 3/2, and then that would be -4. But then it would be plus 5/2. And let's see, 3/2 minus 4 plus 5/2 is 3/2 minus 8/2 plus 5/2. 3 and 5 is 8. Then minus 8/2. Yep, that works. That gives us 0. And this row by this column is going to be 1/2 minus 8 plus 5/2 of 3 is 15/2. Yeah, that works. Okay. So it looks like maybe we do have the inverse. Now we'd have to multiply the second and third rows. I can see pretty well that that's gonna work there. It's gonna work there, and let's see, this one's gonna work there, and it's gonna work there. Okay, in my head I can verify that it seems to be true. So in a rarity, I've done all the arithmetic correctly. So this is A inverse times A equals the identity. And we have verified then that the product E6 down through E1 is the inverse. It has to be, because of if these steps are right, and if I've calculated the elementary matrices right, it has to work. So again, in a rarity, it actually did work. Okay, well, we can, and I think some of that was off camera. So let's just bring this back over here a little bit so we can see it. All I've done is multiplied the inverse matrix, this one, by the original matrix, which is this one, gotten the identity, and I noted that that was A inverse times A equals I, verifying that this is the inverse matrix. Okay, now, we saw previously that our sequence of matrix reduction was to multiply A by E1, that's where we multiplied the first row by 1/2, and that's what E1 does. Then we multiplied the second row by 1/2, that's what E2 does. And then we switched, we added a multiple. What did we do? Well, we subtracted, or added -1 times the second row to the third, that was E3. So, taking these matrices and multiplying them one at a time, always going to the left, we do find that we reduce the matrix A to the identity. The inverse matrix then is this, and we saw that previously. Okay, so if something multiplies A and gives you the identity, that something is the inverse of A. Okay, we notice also, at least we assert, that this product has to equal the identity. Okay, and there's an easy reason for that. E6 inverse times E6 is the identity. And identity here, well, let's multiply the identity by E5, we'll just get E5, and now E5 is next to E5 inverse, and E5 inverse E5 is going to give us the identity. Multiply that identity by E4, and then E4 is next to E4 inverse, and it's going to continue all the way back, so we're just going to get the identity when we're done, showing again that this is the inverse of this. Now, you want to pay attention to the order. You want to understand why the inverse of A has to be in the order E6 through E1. If you do E1 through E6, you don't get the inverse matrix, you don't get the matrix. Okay? If you want to go from E1 through E6, you'll do the inverse matrices. Another thing we'll note, the determinant of our matrix A is 4, isn't it? Okay, well, what's the determinant of this matrix? Okay, well, if we expand by the first column, it's just going to be 1/2 times the determinant of the minor that we see here. That determinant is 3/2. Yeah, 3/2 minus 1, which is 1/2, and we multiply that by the 1/2 here, we get 1/4. The determinant of the inverse is the reciprocal of the determinant of the original matrix. So that's also worth understanding, and just kind of reinforcement of the fact that the determinant of the inverse has to be the reciprocal of the determinant, and we can understand that if we go back to the determinants of the elementary matrices. So let me move this board out of the way. Remember that our inverse matrix was the product E6 down through E1. Okay, and the determinants of these matrices were 1/2, 1/2, 1, and I don't think I even okay, you can verify all these determinants. The only elementary matrix that has a determinant other than 1 is one where you multiply a row by some number other than 1. Okay, so it's only this one and this one, but now the product of the determinants gives you the determinant of the matrix. Now remember, the product of these matrices, if we go E6, E5 down through E1, is the inverse matrix, and the determinants are 1/2, 1/2, 1, 1, 1. They multiply out to 1/4, which is just what we found for the determinant of the inverse matrix. And the determinants of the inverse elementary matrices are just the reciprocals, it turns out, and we can see that it's so. So we have determinants 2, 2, and then the rest of them are all 1. That multiplies out to 4. Well, the inverse matrices, E1 inverse through E6 inverse, give us the original matrix, and the determinants multiply out to 4, which is the determinant of the original matrix.